All right, so welcome back. Today in this video, we're going to be continuing the Geotechnical Engineering section of the Civil FE exam review, and we're going to be focusing specifically on one of the topics that deals with consolidation and differential settlement. So I have a few practice problems for you all today, and I want to go ahead and dive right in. All right, so number one says, using the following details, what is the ultimate consolidation settlement in the soil layer? Total change in void ratio is 0.15. Thickness of soil layer is 8 meters, and the initial void ratio is 0.75. Okay, so let's write out the information that we're given. We're given the initial void ratio, and we're given the total change in void ratio. Okay, so what else are we given? Well, we're given thickness of soil. Okay. Anything else? No, I think that's it. So we're trying to find, what are we trying to find? We're trying to find the ultimate consolidation settlement. Okay, we're trying to find the ultimate consolidation settlement. So what formulas might we need for this? Well, I don't know. I'm going to search consolidation settlement. See if anything pops up. So consolidation settlement. Okay, so one option pops up. All right, so ultimate consolidation settlement in soil layer is known as SULT, which is equal to EV times HS. All right. So what is EV? Well, EV is equal to the change in E total. So based on the notes, E0 is initial void ratio, E0, and then change in E total. So change in total void ratio. The total change in void ratio, right? So I have the total change in void ratio, which is 0.15. I have one. I know what one is, plus E0. Do I know what the initial void ratio is? Yes. 0.75. Okay. So I can get EV. Do I have HS? What's HS? HS is the thickness of the soil layer. Do I have the thickness of the soil layer? Yes. Now it's just a matter of plugging and chugging. Okay. So I know that I'm looking for the ultimate consolidation settlement in the soil layer. So I'm looking for SULT. So SULT equal to E times V times HS. You just have to break it up in pieces, right? All right, so EV is what? EV is equal to the change in the total void ratio divided by 1 plus the initial void ratio. So this is equal to, well, what's the change in E total? total. The total change in void ratio is 0.15. I'll do 0.15 divided by 1 plus E0, which is 0.75. And for that, I get my EV is equal to 0.0857. Okay. Cool there. So we got this value. All right. What is HS? This value. So HS is equal to just the thickness of the soil layer, which is equal to 8 meters. All right. So I have HS, have EV. So now I can get my ultimate consolidation settlement. So I'm just going to plug and chug now. So as ult is equal to EV, which is equal to 0.0857 times my 8 meters is equal to 0.68 meters, or C. So just reading out the problems, figuring out the variables that you have versus the variables that you need. SO was one of the variables that we needed. We also needed EV, and we didn't have it until we went and found what E total was, which is the total change in void ratio. So we figured it out though. All right, let's look at number 2. Number 2 says, what is the correlation between the liquid limit and compression index? Okay. So the information that we're given, I like to write down that to start. So we're given liquid limit and compression index, right? And we're trying to find correlation between the two, right? So to find a formula that we would need to use is I would search, right? I would do compression index to start. All right, there's 2 things that come up for compression index. Okay, compression index and compression index by correlation. Okay. So this is recompression index. And this is compression index. So I think we're just looking at compression index by correlation to liquid limit. Okay, we're not looking at recompression index by correlation to the compression index, right? So recompression index by correlation to liquid limit is CC. So that's I'm assuming CC is compression index. Inversion compression range, CC is equal to, what is CC? I'm assuming CC is compression index, but yeah. Okay, so compression index would be CC, and then recompression index is owned by CR, and then they bring in by correlation to compression index, which is again CC. Okay, so compression index is in fact CC, right? So by correlate, so I know I'm going to need correlation between the liquid limit and the compression index, which is here. So formula I need is CC is equal to 0.009 times LL minus 10. Okay, so let's see here. As liquid, let's test these. As liquid limit increases, compression index increases. So if I just say for the first example, I'll say my liquid limit increases from, we'll just say from 10 to 11. Then what happens? It goes from my CC, if I plug in 10, right? It goes from 0 to 0.009, right? So I know that if I increase my liquid limit, my compression index also increases. So A is correct. As liquid limit decreases, so if I decrease my liquid limit, will my compression index increase? No. As liquid limit increases, then my compression index decreases? No. Not enough information? No. We have it in the handbook. So answer is A. All right, so this concludes the consolidation and differential settlement portion of the geotechnical engineering review. In the next video, we're going to be looking, I thought this concluded it. I lied. This is not concluded. Let's look at number 3. Okay, so number 3 says, what is the time factor of a dually drained soil? Dually drained soil. So the information that we're given that this is dually drained. I'm assuming that means it can be drained on both sides. We're given time, or T. We're given CV, C sub V rather. And then we're also given H, which I'm assuming is the height of the soil. All right, and we need to find the time factor of a dually drained soil. Okay, so where do I start? Well, I would start by searching time factor just to see if that'll help me. Time factor. Okay, there's one option for time factor. I love it. Time factor. Okay. So a lot of this is knowing what to search to. Like if it's something that it doesn't seem like it would be in the handbook or has only a few searches, then that may be a good term to search, right? So if I would just search time, all right, there's probably a lot. Let's just do it to see. If I just search time, there's 250 things that it says time, but time factor is only one. Okay, so where a time factor is T sub V, that's our time factor, is equal to CV times T over H squared dr. Okay, are we in this a soil section? Yes. Okay. So how do we know what well, we were given CV, right? We're given T, which equals 2 seconds. And we're given HDR. Are we given HDR? Well, HDR. So let's look at this. Different types of drainage. All right, so you have one-way drainage down, then your HDR is just your HDR. All right, it goes one way, it drains one way. Let's look at what H, assuming that's your height of drainage, right? Yes. So, another one-way drainage could be it drains up, right? And so it only drains that way. So your height of drainage is just HDR. Now, if you have a dually drained or two-way drainage, it's key to remember, right? It can drain down or up, and you're going to have 2 times the height, right? 2 times the height of the sample, because it can drain both ways. Okay, so now that we know that information, how do we go from there? All right, so the formula that we need is here, where time factor is, zoom in there real quick, TV is equal to CV times T over HDR. This is squared. Right. So, HDR in this case, since it's dually drained, is going to be what? 2, or this height, complete HDR is going to be 2 times H, right? And so your HDR in this case is going to equal to 2 times 3. Okay, so HDR, the amount of distance that it can drain, is going to be 6 meters. Okay. What about, we know CV, we know T, and we know our HDR now. So now we can solve for this. So time factor is equal to, CV is 0.1 times 2 seconds. Divided by our 6 meters. Square that, and we get a time factor of 0.005. So I guess it's unitless. It is a factor. So units, definitely, your units don't have to necessarily cancel in this case. All right, so that concludes our consolidation and differential settlement. In the next video, we will be looking at slope stability. So see you in the next video.